Venus just received something it hasn't encountered in billions of years, and we almost missed it. On November 3rd, 2025, while most of the world was focused on what happened at Mars a month earlier, an interstellar comet delivered a package to Venus that shouldn't exist in its atmosphere. And here's what makes this impossible to ignore. The materials that arrived molecules from outside our solar system can actually survive in Venus's sulfuric acid clouds. Think about that for a moment. Venus, the planet where Soviet landers melted within hours, the planet with surface temperatures hot enough to melt lead, atmospheric pressure equivalent to being a kilometre underwater, and clouds made of battery acid. That Venus. It just received organic molecules, water and refined metals from an object that spent 10 billion years travelling through interstellar space. And instead of being instantly destroyed, some of these materials are persisting, reacting, transforming Venus's atmospheric chemistry in ways we're only beginning to understand. This isn't science fiction. This is November 2025, and it's happening right now while you're watching this. Venus's upper atmosphere is currently processing chemistry that arrived from beyond our solar system just weeks ago. The cloud layers that have remained essentially unchanged for billions of years are now circulating molecules that have never been part of Venus's natural system. And unlike Mars, where materials deposited on the cold surface and waited for excavation, Venus's chemistry is active, transforming, reacting, exploring new pathways immediately. But before we understand what this means, we need to establish exactly what happened on November 3rd. The interstellar comet 3I-ATLAS, the same object that passed Mars on October 3rd, made its second close approach to an inner solar system planet. The distance was 0.65 astronomical units, roughly 97 million kilometres. That's close enough for Venus's gravity to capture material from the comet's coma. That's close enough for the thin envelope of sublimated gas and dust surrounding the comet's nucleus to intersect with Venus's upper atmospheric layers. That's close enough for an exchange of materials between an interstellar visitor and a planet that hasn't received external chemistry in eons. The timing matters more than you might realise. When 3I-ATLAS passed Mars on October the 3rd, Mars presented a thin atmosphere and a cold, inert surface. Materials arrived, settled, and essentially froze in place, waiting. But Venus is different. Venus has an atmosphere 93 times more massive than Earth's. Venus has wind speeds in the upper atmosphere reaching 100 meters per second, creating a global superrotation where clouds circle the entire planet in just 4 Earth days. Venus has temperatures at cloud level ranging from 0 to minus 60 degrees Celsius, cold enough for chemistry to occur, warm enough for reactions to proceed. And most critically, Venus has sulfuric acid clouds that are both incredibly corrosive and paradoxically capable of preserving certain organic molecules we never expected to survive there. When 3I-ATLAS swept past Venus, its coma extended millions of kilometers into space. The exact composition varied with distance from the nucleus, but as we established from the Mars encounter, the comet was actively ejecting specific materials, water at rates exceeding 120 metric tons per hour, hydrogen cyanide at approximately 80 grams per second, carbon monoxide at similar rates, and something nobody predicted, spectroscopic evidence suggesting unusual nickel enrichment relative to iron, with the exact separation mechanism remaining uncertain. Venus's gravitational field captured a fraction of these materials. Not all of it, most escaped into space, or was deflected by solar wind, but enough. Estimates suggest somewhere between 3 and 10% of the nearby outgassing material intersected Venus's gravitational and atmospheric capture zones. Here's where the geometry becomes critical. Mars's encounter was partially glancing the comet's trajectory swept past Mars at an angle that limited direct interaction time. Venus's encounter was more favourable. The comet's path placed Venus closer to the outgassing stream's centre. The materials arriving at Venus weren't just the diffuse outer edges of the coma, they included denser concentrations from regions closer to the nucleus. This means higher concentrations of everything water, hydrogen cyanide, organics, metals arriving at Venus compared to what Mars received. And unlike the Mars encounter, which had multiple spacecraft from different space agencies positioned to observe and create redundant measurements, the Venus encounter was documented primarily by a single spacecraft, JAXA's Akatsuki orbiter. This creates a limitation we need to acknowledge immediately. NASA's Parker Solar Probe was in a different part of its orbit during the encounter. ESA's Bepi Colombo, travelling toward Mercury, wasn't positioned for detailed Venus observations. Akatsuki recorded data during the encounter window, and that data has been transmitted back to Earth and is currently being analysed. But we don't have the multi-spacecraft verification that made the Mars observations so robust. Our understanding of what actually happened depends more heavily on interpretation of limited data, on models that predict how Venus's atmosphere should respond, and on the chemistry we know must occur when these materials meet Venus's clouds. What we know with certainty is this: 3I-ATLAS passed Venus at a distance, allowing material transfer. The comet was actively outgassing at rates consistent with its late October activity levels. Venus's atmosphere, being thick and gravitationally bound, would capture a measurable fraction of that material. The upper atmospheric layers would be the first point of contact where incoming molecules collide with atmospheric gases and begin slowing down, integrating into Venus's circulation patterns. What we don't know yet, what the data currently being analysed will tell us, is the specific concentration at which materials arrived, the exact chemical pathways they followed once integrated into the clouds, and the atmospheric system's immediate response. But here's what makes this encounter fundamentally different from anything Venus has experienced in geological timescales: external chemistry. Venus's atmosphere operates as a closed system. The materials circulating in those sulfuric acid clouds come from Venus's surface, Venus's geology, and Venus's ongoing photochemical processes driven by solar ultraviolet radiation. Nothing arrives from outside. The system is in equilibrium with itself. Every molecule that rises from the surface eventually returns. Every photochemical product eventually recombines or breaks down into components that feed back into the cycle. Venus's atmospheric chemistry has been running the same loops, the same reactions, the same pathways for billions of years. Stable, predictable, isolated, until November 3rd. The materials 3I-ATLAS delivered aren't in equilibrium with Venus's existing chemistry. They're foreign, reactive, and they carry information chemical structures and elemental compositions from environments completely unlike anything Venus has experienced since its formation. Hydrogen cyanide, for example, doesn't occur naturally in Venus's atmosphere in significant quantities. When it arrives from the comet, it represents genuinely new chemistry. Water vapour, while present in Venus's atmosphere in trace amounts, arrives from the comet in concentrations that temporarily elevate local humidity. Refined nickel, which should not exist in Venus's clouds at all, suddenly becomes part of the atmospheric mix, carried in dust grains, and potentially dissolving into sulfuric acid droplets. These materials don't sit passively once they arrive. Venus's atmosphere is too dynamic for that. Within hours of arrival, atmospheric circulation begins distributing the materials horizontally around the planet and vertically through the cloud layers. Within days, photochemistry begins transforming the molecules. Solar UV radiation breaks chemical bonds, creates reactive radicals, drives reactions that wouldn't occur in darkness. Within weeks, the entire atmospheric system has been exposed to and begun processing these foreign materials. Venus's chemistry, so stable for so long, has been perturbed. The system is responding. And right now, in late November 2025, that response is actively unfolding in Venus's upper atmosphere. The question isn't whether Venus changed, it did. The question is what Venus is doing with the chemistry it received, how long the changes persist, and whether anything unexpected emerges from the interaction between sulfuric acid clouds and molecules from interstellar space. That's what we're about to explore, and the implications reach far beyond Venus itself. To understand what 3I-ATLAS just disrupted, you need to understand what Venus's atmosphere actually is beneath the simplified descriptions we usually hear. Yes, it's hot. Yes, it's acidic. But Venus's atmospheric chemistry is far more intricate than hellish wasteland suggests, and that intricacy is precisely why the introduction of external materials matters so profoundly. Venus's atmosphere isn't a single uniform layer of sulfuric acid and carbon dioxide. It's a vertically stratified system with distinct chemical zones, each operating at different temperatures, pressures, and compositions. Think of it like an ocean. With layers, the surface waters are different from the thermocline, which is different from the deep ocean. Venus's atmosphere has similar stratification, and when materials from 3I-ATLAS arrived, they didn't interact with one uniform environment. They encountered multiple chemical zones simultaneously, each responding differently. Start at the top, where the comet's materials first make contact. The upper cloud layer extending from roughly 60 to 70 kilometers altitude consists of sulfuric acid droplets that are relatively dilute between 50 and 75% concentration. At these altitudes, temperatures hover around 0 to minus 20 degrees Celsius, cold enough for water to condense into ice crystals, cold enough for certain organic molecules to remain stable longer before photochemistry destroys them. The atmospheric pressure here is low, about 1/10 of Earth's surface pressure, which means molecules have longer mean free paths before colliding with others. This is important because reaction rates depend on collision frequency. Lower pressure means slower reactions, which means molecules persist longer. This upper cloud layer is also where most of the atmospheric mixing happens. Winds driven by temperature gradients and pressure differences create circulation patterns that redistribute atmospheric contents around the planet every 4 Earth days. Materials arriving here don't stay localized, they're immediately caught up in circulation and begin spreading globally. Drop down to 50 to 60 kilometers altitude and you enter the middle cloud layer. Here, sulfuric acid concentrations increase to 75 to 90%. Temperatures drop further to minus 20 to minus 40 degrees Celsius. This is where most of the visible atmospheric features occur, the Y-shaped patterns and vortices that spacecraft cameras capture when imaging Venus. The middle cloud layer is denser, the chemistry more aggressive. Molecules that survived in the upper layer begin encountering higher acid concentrations here. Some break down, some transform into different compounds, some incorporate into the acid droplets themselves, becoming part of the liquid solution rather than remaining as separate gas phase molecules. Below that, 45 to 50 kilometers altitude, lies the lower cloud layer. Sulfuric acid concentrations reach 80 to 90%. Temperatures are minus 40 to minus 60 degrees Celsius. Pressure is approaching 1 Earth atmosphere, and the environment becomes increasingly hostile to organic chemistry. This is the zone where most molecules that survive the upper layers finally break down or transform into stable end products. The lower cloud layer acts as a chemical terminus for many atmospheric processes. Materials that make it this deep are either incorporated into precipitation that eventually returns to the surface, or they're broken down into components that rise back up through convection to begin the cycle again. Beneath all 3 cloud layers, from 0 to 45 kilometers altitude, lies what's optimistically called the clear atmosphere, though clear is misleading. Visibility is limited by hazes and aerosols. The atmosphere here is dominated by carbon dioxide and nitrogen, with temperatures increasing dramatically toward the surface. By the time you reach Venus's surface at 460 plus degrees Celsius, chemistry operates under conditions we'd recognize from industrial furnaces, not planetary atmospheres. Materials don't survive here, they're incinerated, decomposed, or absorbed into surface geology. Now, why does this layering matter for our story? Because when 3I-ATLAS's materials arrive, they don't all end up in the same chemical environment. Lighter molecules like water vapor and hydrogen cyanide gas penetrate deeper into the atmosphere before atmospheric drag fully decelerates them. Heavier particles, dust grains containing nickel, silicates, and other minerals decelerate faster and remain in the upper atmospheric layers longer before settling. Each type of material encounters different chemical conditions based on where it ends up in this stratified system. Water arriving at the upper cloud layer meets dilute sulfuric acid and cold temperatures. It condenses, forms mixed droplets, and releases heat. Hydrogen cyanide arriving at the middle cloud layer dissolves into more concentrated acid and begins hydrolyzing, breaking down into ammonia and formic acid through reactions with water molecules in the acid solution. Nickel-containing dust grains, when they encounter sulfuric acid at any level, react to form nickel sulfate compounds that dissolve into the droplets, becoming part of the liquid phase. Each material follows its own pathway through Venus's atmospheric chemistry. Each transformation creates products that themselves have chemical identities and behaviors. And all of this happens within a system that's been running essentially unchanged for billions of years. Venus's atmospheric chemistry operates as a conveyor belt. Sulfur dioxide rises from the surface, or is produced through photochemical reactions in the lower atmosphere. Solar ultraviolet radiation breaks it down in the upper atmosphere, producing sulfuric acid through reactions with oxygen and water. The sulfuric acid condenses into droplets, forming the cloud layers. Those droplets grow, coalesce, and eventually precipitate downward. Though on Venus, precipitation doesn't reach the surface. The intense heat in the lower atmosphere causes the droplets to evaporate before they can fall all the way down. releasing their sulfuric acid back into gaseous form. The sulfur dioxide regenerates and rises again. The cycle repeats. This has been happening for eons, creating the stable sulfuric acid cloud layers that define Venus's appearance and chemistry. The system is in equilibrium because it's closed. Every component comes from Venus itself. Every reaction product eventually feeds back into the system. There are no external inputs. No asteroids delivering water, no comets injecting organics, no meteorite flux bringing metals. Venus's atmosphere is isolated from external influence, operating purely on its own internal cycles and solar energy input. This equilibrium creates predictability. Scientists studying Venus know what to expect in the clouds: sulfuric acid droplets, trace water vapour, carbon dioxide, sulfur dioxide, some carbonyl sulfide, noble gases like argon inherited from Venus's formation. The concentrations vary slightly with altitude and location, but the overall composition is understood and stable, until materials from 3I-ATLAS integrate into this system. Suddenly, Venus's atmosphere contains molecules it hasn't processed in billions of years. Hydrogen cyanide appears in concentrations elevated above background levels. Water vapour increases locally where the comet's materials were captured. Nickel compounds, which have no business being in Venus's clouds, are now circulating in the upper atmosphere. These aren't equilibrium components, they're perturbations. They don't fit into the existing chemical cycles because they didn't originate from Venus's geology or photochemistry. And when non-equilibrium chemistry enters a system that's been stable for billions of years, the system responds. It reacts. It tries to incorporate the new materials or break them down into components it can process. The sulfuric acid clouds that have been Venus's defining feature are now hosting chemistry they've never encountered. Water mixing with sulfuric acid dilutes the acid concentration locally, creating zones where the chemical environment is less aggressive. Hydrogen cyanide hydrolyzing into ammonia creates basic compounds, bases in an overwhelmingly acidic environment. Ammonia neutralizes acid. It forms salts like ammonium sulfate, which are stable and can persist for weeks before other processes break them down. Nickel ions dissolving into droplets give those droplets catalytic properties they didn't have before. Organic molecules produced from hydrogen cyanide breakdown accumulate in regions where photochemistry hasn't yet destroyed them. This is no longer the Venus atmosphere of early November 2025. It's a slightly different chemical system, perturbed away from equilibrium, actively exploring reactions and pathways that don't occur during normal operations. The changes might be small in absolute terms. We're talking about parts per billion concentration increases for most of these materials. But in a system as chemically active and dynamic as Venus's upper atmosphere, even small changes can propagate. They can create cascades of secondary reactions. They can produce compounds that wouldn't normally exist, which themselves go on to react with other atmospheric components. The atmosphere doesn't simply absorb the new materials and return to normal. It processes them, transforms them, and in doing so, temporarily becomes a different chemical system. And understanding what that different system looks like, what reactions are occurring, what products are forming, how long the perturbation persists, requires the data that's currently being analysed from Akatsuki's observations during the encounter. We're waiting for confirmation of what theory and chemistry tell us must be happening. But the framework is clear. Venus received materials from outside its closed system, and those materials are now driving chemistry Venus hasn't experienced in geological timescales. Let's be specific about the chemistry that arrived at Venus on November 3rd, because precision matters when we're discussing atmospheric changes at this scale. By early November 2025, 3I-ATLAS had already passed its closest approach to the Sun. Perihelion occurred on October 29th, and the comet was beginning its recession back toward the outer solar system. But receding doesn't mean dormant. Comets remain active for weeks or months after perihelion as solar heating continues sublimating ice from the nucleus. The rates decline compared to peak activity, but they're still substantial. And the materials being ejected are the same suite of molecules and compounds the comet has been producing since August. Water, hydrogen cyanide, carbon monoxide, and the unexpected component that makes this story so remarkable: refined nickel separated from iron through natural processes that mimic industrial chemistry. Water was still flowing from the comet at rates around 120 to 130 metric tons per hour by early November. This represents a decline from the peak rates of 140 plus metric tons per hour observed in October, but it's still an enormous mass flux. For comparison, a commercial jetliner weighs about 180 metric tons fully loaded. 3I-ATLAS was ejecting the equivalent of a jetliner's mass in water every hour and a half. Most of this water escapes into space, spreading outward in the comet's tail and coma. But when the comet passes close to a planet with sufficient gravity and a substantial atmosphere, a fraction gets captured. Venus's capture efficiency depends on multiple factors: the relative velocities of the comet and planet, the angle of approach, the density of the comet's coma at Venus's distance, and Venus's atmospheric interaction cross-section. Models suggest capture rates between 3 and 10% for materials in the vicinity during the encounter window. Apply that to the water flux, and Venus received somewhere between 3 and 12 metric tons of water, spread over the several hours when the comet's influence was strongest. That might not sound like much compared to Venus's total atmospheric water content, which is measured in thousands of metric tons. But distribution matters. This water didn't arrive uniformly across the planet. It arrived at specific locations where Venus's geometry during the encounter placed its atmosphere in the comet's outgassing stream. Local concentrations at the arrival points would have been significantly elevated enough to create measurable changes in humidity, cloud droplet composition, and reaction rates for processes that depend on water availability. Hydrogen cyanide continued its remarkable exponential increase through October. By the time perihelion occurred on October 29th, HCN production had reached approximately 75 to 100 grams per second, based on extrapolation from earlier measurements. This is extraordinary for a comet. Most comets produce HCN at rates of a few grams per second, even at peak activity. 3I-ATLAS was producing orders of magnitude more, suggesting unusual composition or unusual sublimation processes driven by the comet's interstellar origin and the extreme temperature changes it experienced approaching the Sun after billions of years in cold storage. By November 3rd, during the Venus encounter, HCN production had stabilized around 80 to 85 grams per second. Over a 4 to 6 hour encounter window, the period when Venus's gravity and atmospheric capture were most effective, that translates to roughly 1.2 to 1.8 kilograms of hydrogen cyanide delivered to Venus. Hydrogen cyanide is not a normal component of Venus's atmosphere. It exists in trace amounts produced through photochemical pathways, but concentrations are negligible under normal conditions. The arrival of kilograms of HCN represents a genuine chemical novelty. And unlike water, which Venus's atmosphere already contains and knows how to process, HCN brings chemistry. Venus's system hasn't dealt with in its current atmospheric state. HCN is a precursor to amino acids. It's a building block for nucleotides. It's one of the key molecules astrobiologists look for when assessing prebiotic potential. And it just arrived at Venus in concentrations high enough to create localized environments where HCN-driven chemistry can proceed before photochemistry destroys it. Carbon monoxide was also being ejected at rates comparable to HCN, somewhere in the 60 to 70 grams per second range, based on spectroscopic signatures detected by ground-based observatories. Over the Venus encounter window, that's roughly 0.9 to 1.7 kilograms of CO arriving. Carbon monoxide exists in Venus's atmosphere naturally, but at concentrations around 20 parts per million. The comet's delivery temporarily increases this locally, creating enriched zones where CO concentrations are elevated above background. This matters for specific chemical reactions, particularly catalytic processes, where CO acts as a reactant or substrate. And then the nickel. The refined nickel that spectroscopic analysis revealed was being ejected preferentially separated from iron, an anomaly that suggests the comet underwent processes resembling the industrial Mond process, where nickel forms volatile nickel carbonyl compounds that separate from non-volatile iron. By November 3rd, nickel ejection rates were likely in the range of 3 to 4.5 grams per second, slightly declined from the peak rates observed in October. Over the encounter window, that's 50 to 110 grams of nickel arriving at Venus. This is a tiny mass compared to atmospheric scales, but nickel's chemical significance far exceeds its mass. Nickel is a catalyst. It accelerates specific reactions without being consumed. Even trace amounts can have disproportionate effects on chemical systems where those reactions are occurring. When nickel arrives at Venus and encounters sulfuric acid, it doesn't remain as metallic nickel. It reacts immediately. Nickel dissolves in sulfuric acid, forming nickel sulfate, a soluble compound that integrates into the liquid droplets. Those droplets, now containing nickel ions, gain catalytic properties. Reactions that would proceed slowly or not at all in pure sulfuric acid can be accelerated when nickel is present. The water-gas shift reaction carbon monoxide plus water-producing carbon dioxide plus hydrogen is catalyzed by nickel. Fischer-Tropsch type reactions that build longer carbon chains from simple precursors can be catalyzed by nickel surfaces. Venus's sulfuric acid droplets have just acquired an ingredient that enables chemistry they couldn't perform before. Beyond these major components, the comet was delivering a suite of minor species, organic compounds synthesized in the coma through reactions between HCN, water, and other molecules, sulfur-bearing compounds from cometary dust, silicates and mineral grains, trace metals beyond nickel. The complete compositional inventory wasn't documented because spectroscopy prioritizes the most abundant species with the strongest signatures. But comets are chemically complex, and everything the nucleus releases becomes part of the delivery package. Venus received not just pure water and HCN, but a mixture, a chemical cocktail containing dozens or hundreds of distinct molecular species, all arriving simultaneously, all beginning to interact with Venus's existing atmospheric chemistry the moment they're captured. This represents fundamental novelty. Venus's atmosphere hasn't received an external chemical delivery in billions of years. The materials now circulating in the upper cloud layers are genuinely foreign. They didn't originate from Venus's surface or from photochemical breakdown of atmospheric gases. They came from outside, from an object that formed in a different star system, travelled through interstellar space for eons, and happened to pass through our inner solar system at precisely the right time and trajectory to intersect Venus. The chemistry that arrived carries information about cometary processes, about interstellar conditions, about chemical pathways that operated during the comet's formation billions of years ago. And now that chemistry is interacting with Venus, being transformed by sulfuric acid and solar radiation, producing compounds that blend interstellar heritage with Venusian processing. By late November 2025, the initial arrival has passed. The materials are now integrated into Venus's atmospheric circulation. They're reacting. They're being broken down and recombined. They're creating a temporary chemical state that Venus hasn't experienced in geological memory. And the data documenting this transformation exists, recorded by Akatsuki during the encounter and transmitted back to Earth, waiting for analysis to reveal exactly how Venus's chemistry responded to this unexpected gift from interstellar space. Understanding where the comet's materials ended up in Venus's atmosphere requires understanding how Venus's gravity and atmospheric dynamics capture and redistribute incoming matter. This isn't like dropping objects onto a solid surface where they stay where they land. Venus's atmosphere is a fluid system, constantly circulating, constantly mixing materials vertically and horizontally. When materials from 3I-ATLAS entered Venus's sphere of influence, they didn't simply fall straight down. They were captured, decelerated, and integrated into atmospheric flow patterns that immediately began carrying them away from their initial arrival points. The distribution of these materials across Venus's atmosphere determines where the highest concentrations exist, where the most active chemistry is occurring, and where spacecraft instruments are most likely to detect the changes. Venus's gravitational sphere of influence, the region where Venus's gravity dominates over the Sun's, extends roughly 1 million kilometers outward from the planet. This is a substantial volume of space, and when 3I-ATLAS passed at 97 million kilometers distance, portions of the comet's coma entered this sphere. The coma at that distance was relatively diffuse. The densest concentrations of gas and dust remain close to the nucleus, but even diffuse material becomes significant when you're talking about Venus's atmospheric capture efficiency. The comet's outgassing creates a directional stream. Materials aren't ejected uniformly in all directions. They're preferentially ejected away from the nucleus on the sunward side, where solar heating is most intense. This creates a structure where the highest densities exist in a cone-shaped region behind the nucleus from the Sun's perspective. Venus's position relative to this outgassing cone during the November 3rd encounter determined which portion of the coma Venus's atmosphere intersected. If Venus was positioned directly in the outgassing stream, capture efficiency would be higher. If Venus was positioned at the edge of the coma, capture would be lower. Orbital mechanics and the specific trajectory of 3I-ATLAS placed Venus in a favourable position not directly in the densest part of the stream, but close enough that material densities were elevated compared to the diffuse outer coma. This geometry explains why Venus likely captured more material per unit area than Mars did during its October encounter, despite Mars being closer to the comet at that time. Once materials enter Venus's outer atmosphere, the thermosphere above 100 km altitude deceleration begins immediately. Molecules entering at high velocity collide with atmospheric gas molecules. Each collision transfers kinetic energy, slowing the incoming particle. Lighter molecules like water vapour and hydrogen cyanide decelerate more gradually, penetrating deeper before atmospheric drag fully captures them. Heavier particles, dust grains containing nickel and minerals, experience stronger drag and decelerate faster, settling into the upper atmospheric layers without reaching the deeper cloud regions. This creates a natural stratification, where different materials accumulate at different altitudes based on their mass and aerodynamic properties. By the time materials reach the cloud layers at 45 to 70 km altitude, they've lost most of their original velocity. They're now moving at speeds determined by local atmospheric winds rather than their arrival trajectory. They've been integrated into Venus's circulation system, and from this point forward, atmospheric dynamics control where they go. And Venus's atmospheric dynamics are dominated by one extraordinary feature: superrotation. Despite Venus's incredibly slow planetary rotation, one Venusian day lasts 243 Earth days. The upper atmosphere circulates around the entire planet in just 4 days. Winds at cloud level reach 100 meters per second, driven by complex interactions between solar heating, pressure gradients, and atmospheric wave dynamics. This superrotation means materials introduced at any specific location don't remain localized for long. Within hours, they're carried hundreds or thousands of kilometers around the planet by horizontal winds. But circulation isn't just horizontal. Venus's atmosphere also exhibits strong vertical circulation patterns driven by the Hadley cell, a global-scale circulation where warm air rises at the equator or subsolar point, flows toward the poles at high altitude, and descends at higher latitudes before returning equatorward at lower altitudes. This vertical circulation couples with the horizontal superrotation to create three-dimensional mixing. Materials introduced into the upper atmosphere are simultaneously carried around the planet horizontally and transported poleward or equatorward vertically. Over days to weeks, this circulation distributes incoming materials throughout the atmospheric volume, though not uniformly. Certain regions, particularly downwelling zones where air descends, can accumulate higher concentrations as materials are brought down from higher altitudes and concentrated by compression. The specific arrival location on November 3rd matters enormously for understanding the initial distribution. Venus's position in its orbit and the encounter geometry determined whether materials arrived on Venus's day side or night side at low or high latitudes during local morning or afternoon. This determines which atmospheric circulation cells initially captured the materials and where they were first carried. November 3rd, 2025, based on Venus's orbital position, placed the encounter during Venus's late morning solar time at the arrival point. This means the region was under solar illumination, actively being heated, and experiencing upwelling circulation that would carry incoming materials upward into the superrotating layers before distributing them globally. Temperature plays a critical role in how materials behave once integrated. The upper cloud layer, where temperatures range from 0 to minus 20 degrees Celsius, is cold enough for water to condense into ice crystals, and for certain organic molecules to remain stable longer before photochemistry destroys them. As materials circulate through this layer, they can persist for extended periods, potentially weeks, before being transported to warmer or more UV-exposed regions where breakdown accelerates. The middle cloud layer, with temperatures of minus 20 to minus 40 degrees Celsius, is colder still, but sulfuric acid concentrations are higher. Materials reaching this layer encounter more aggressive chemistry. Some molecules that survived in the upper layer break down here. Others transform into different compounds through reactions with the concentrated acid. Photochemistry begins immediately for any molecules exposed to sunlight in the upper atmosphere. Solar ultraviolet radiation breaks chemical bonds, creating reactive radicals that go on to form new compounds. Water molecules photodissociate into hydrogen and oxygen atoms. Hydrogen cyanide breaks down into cyanide radicals and hydrogen, but photodissociation doesn't mean instant elimination. The reaction products are often as chemically interesting as the original molecules, and they can recombine with other atmospheric constituents to form entirely new species. Hydrogen atoms from water photodissociation can react with carbon dioxide to form formic acid. Cyanide radicals can react with ammonia-like compounds to form more complex nitrogen-bearing organics. The photochemistry drives a cascade of transformations that ultimately breaks down the comet-delivered materials. But the intermediate products along that cascade are themselves part of the atmospheric chemistry Venus is now experiencing. The timescale for global mixing is roughly 1 to 2 weeks. That's how long it takes for materials introduced at one location to be distributed throughout the upper atmospheric layers by the combined action of superrotation and Hadley cell circulation. By late November 2025, several weeks after the encounter, the initial localized concentrations have been dispersed. Materials are now present throughout Venus's upper atmosphere at low but measurable concentrations, with elevated levels persisting in certain regions where circulation patterns have concentrated them. Downwelling zones at higher latitudes likely show higher concentrations. Polar regions, where atmospheric dynamics are complex and somewhat isolated from the main circulation, might retain localized pockets of elevated material. Detecting these changes requires spacecraft observation specifically targeting the relevant atmospheric regions and chemical species. Akatsuki's instruments designed to study Venus's atmospheric dynamics and composition are capable of measuring trace gases and cloud properties. If the data analysis reveals elevated concentrations of water vapor, hydrogen cyanide, or nickel compounds in the regions where models predict they should appear, that's confirmation the capture and distribution occurred as theory suggests. If the data shows no significant changes or concentrations below detection limits, it indicates either lower capture efficiency than estimated or faster breakdown and dispersion than models predicted. Either outcome teaches us something valuable about how Venus's atmosphere responds to external inputs. But the most important point is that the data exists. The measurements were made. Akatsuki observed Venus's atmosphere during and after the encounter. The information needed to answer these questions has been recorded and is currently being processed, calibrated and analysed. We're in the waiting phase, the period between observation and publication, where scientific analysis transforms raw data into understanding. And that understanding will definitively tell us how Venus's atmospheric chemistry changed in response to an interstellar comet's delivery of materials from beyond our solar system. Here's where everything you thought you knew about Venus gets turned upside down. For decades, the scientific narrative has been clear and consistent. Venus is sterile. Anything organic arriving there gets instantly destroyed by the sulfuric acid clouds, the intense UV radiation, the high temperatures. Venus represents the opposite of habitability, a cautionary tale of what happens when planetary conditions go catastrophically wrong. Life could never emerge there. Complex chemistry couldn't persist there. Venus is a dead world where chemistry goes to die. Except that's not entirely true. Research published in March 2024 in the journal Astrobiology has revealed something that changes our understanding of what Venus's atmosphere can actually support. Researchers tested 20 biogenic amino acids, the exact molecules that form proteins in all Earth life, in sulfuric acid solutions designed to mimic Venus's cloud chemistry. The concentrations, temperatures and exposure times matched what we expect in Venus's upper and middle cloud layers. The hypothesis going in was that most or all of these amino acids would be destroyed or heavily degraded by the acid. That's what conventional wisdom predicted. But the results told a very different story. Out of 20 amino acids tested, 11 showed complete stability. No reaction. No degradation. They remained intact in sulfuric acid concentrations that should have destroyed them. 8 additional amino acids showed stability, even after undergoing partial chemical alteration, meaning they transformed into related compounds, but didn't decompose into unrecognizable fragments. Only 1 amino acid out of 20 showed significant instability and breakdown. Think about what this means. 19 out of 20 amino acids either survived completely or survived in recognizable altered forms in sulfuric acid at Venus cloud conditions. These aren't exotic molecules. These are the building blocks of life as we know it, and they can persist in Venus's clouds. This finding demolishes the assumption that Venus's sulfuric acid instantly sterilizes all organic chemistry. It doesn't. Sulfuric acid is selective. It attacks certain molecular structures aggressively, while leaving others essentially untouched. The amino acids that survived are precisely the types of molecules that 3I-ATLAS was delivering to Venus on November 3rd. Hydrogen cyanide breaks down in water and acid to form amino acids and other organic precursors. Those products, the ones arriving at Venus from cometary chemistry, are now known to be stable in sulfuric acid at cloud temperatures. They don't get eliminated immediately. They persist. They remain available for further chemistry. They can participate in reactions, explore complexity, build toward more sophisticated molecular structures before photochemistry or circulation eventually brings them to regions where they finally break down. This changes the entire framework for understanding what happened on November 3rd. The hydrogen cyanide delivered by 3I-ATLAS didn't arrive and vanish. It arrived and began a series of transformations, each step potentially producing stable or semi-stable products that can persist for meaningful timescales. When HCN dissolves in dilute sulfuric acid in Venus's upper clouds, it hydrolyzes, reacts with water to break down into ammonia and formic acid. Ammonia is a base. In an overwhelmingly acidic environment, bases neutralize acid locally. They create microenvironments within the droplets where pH is elevated, where acidity is reduced, where chemistry that couldn't occur in pure sulfuric acid becomes possible. These neutralized zones are where organic chemistry can be most active, where amino acids can form, where more complex molecules can assemble without being immediately attacked by acid. The sulfuric acid droplets become chemical reactors operating under conditions we never expected could support prebiotic chemistry. Each droplet contains a mixture: sulfuric acid, water, dissolved organic molecules from the comet, ammonia produced by HCN breakdown, formic acid, and trace amounts of nickel compounds that we'll discuss shortly. The chemistry inside these droplets isn't in equilibrium. Energy is being input constantly through solar radiation. Temperature fluctuations occur as droplets rise or fall through atmospheric layers, experiencing different thermal conditions. The droplets are isolated from each other. They're discrete reaction vessels floating in the atmosphere, so reactions in one droplet can proceed independently of what's happening in neighbouring droplets. This creates a massively parallel chemical exploration, where billions of droplets are simultaneously testing different reaction pathways, producing different products, exploring different possibilities. Some droplets will produce nothing of interest, random combinations of molecules that don't lead anywhere chemically significant. But some droplets might stumble onto pathways that produce more complex organics. Small peptides formed from amino acids linking together, nucleotide precursors assembling from HCN-derived products, lipid-like molecules forming from reactions between organic acids. None of this constitutes life. None of this creates biology. But it represents complexity chemical structures more sophisticated than simple precursors, exhibiting organization and patterns that don't occur in random chemical mixtures. It's the kind of chemistry that astrobiologists study when trying to understand how life's building blocks could have emerged from non-living chemistry on early Earth or other worlds. And this is happening right now in Venus's clouds. Not as a hypothetical future scenario, not as a possibility we might observe decades from now. This chemistry began the moment 3I-ATLAS's materials integrated into Venus's atmosphere on November 3rd. For weeks now, sulfuric acid droplets enriched with cometary organics have been circulating through Venus's upper atmosphere, reacting, transforming, potentially assembling complexity. The photochemistry that will eventually destroy these molecules is also underway. UV radiation is constantly breaking bonds and creating radicals, but the timescale for complete photochemical destruction is weeks to months, and during that window the organic chemistry is active. Here's the piece that makes this even more remarkable. Venus's clouds have long been proposed as a potential habitat for hypothetical microbial life. Not because sulfuric acid is friendly to biology, it's not, but because the specific conditions in Venus's upper clouds mirror certain parameters that life requires. Temperatures are moderate. Liquid water exists in the droplets mixed with sulfuric acid. Sunlight provides energy. The clouds are stable enough that microbes could potentially remain airborne indefinitely, circulating with the atmospheric flow. The main objection has always been chemistry. What would these microbes eat? Venus's atmosphere doesn't naturally contain organic molecules in meaningful quantities. Any hypothetical life would have to synthesize everything from atmospheric carbon dioxide and nitrogen, which is energetically expensive and difficult. But if Venus regularly receives organic chemistry from external sources, comets, meteorites, interplanetary dust. Then the clouds would have access to raw materials that make the chemistry less prohibitive. 3I-ATLAS just delivered a substantial bolus of exactly those raw materials: hydrogen cyanide and its breakdown products, amino acids, organic precursors. If hypothetical microbes exist in Venus's clouds, they've just received food. If they don't exist, which is far more likely given the extreme conditions, the chemistry that could lead toward their emergence has just been seeded. Does this mean life will suddenly appear? Absolutely not. The gap between complex organic chemistry and actual biology is enormous, involving countless additional steps and requirements. But the gap is smaller now than it was before November 3rd. Venus's clouds are currently exploring chemical territory they don't normally access, courtesy of an interstellar visitor. The implications extend beyond Venus. If sulfuric acid clouds can support prebiotic organic chemistry, if molecules can survive and react and build complexity in environments we thought were sterile, then our understanding of where chemistry relevant to life can operate expands dramatically. Acidic environments on other worlds become less immediately dismissible. Atmospheric chemistry in general becomes a more interesting venue for prebiotic processes. The universe's inventory of places where complex chemistry might emerge grows larger, and all of this stems from recognizing that Venus's sulfuric acid isn't the universal destroyer we assumed it was. It's selective. It preserves certain structures while attacking others, and the structures it preserves happen to include many of the building blocks necessary for life. That's not coincidence, it's chemistry. And chemistry, as we're learning, is far more permissive and creative than simplified models suggest. Venus's atmosphere is currently demonstrating that creativity, processing materials from an interstellar comet, undergoing reactions that haven't occurred there in billions of years, and potentially producing complexity we won't fully understand until the observational data is analysed and published in the months ahead. Now let's discuss the ingredient that makes Venus's current atmospheric chemistry genuinely unprecedented: catalytic nickel. When refined nickel from 3I-ATLAS entered Venus's sulfuric acid clouds, it didn't just arrive as a passive trace element. Nickel is chemically active. It's one of nature's most effective catalysts, and its arrival at Venus introduces a capability the atmosphere has never possessed the ability to accelerate specific reactions that would otherwise proceed so slowly they're effectively impossible. Understanding what nickel can do in Venus's clouds requires understanding catalysis itself, because this is where the story shifts from interesting chemistry to potentially transformative chemistry. Catalysts work by providing alternative reaction pathways that require less energy than the uncatalyzed reaction. Think of a chemical reaction as climbing a mountain. Reactants start in a valley, and products are in another valley on the far side. The uncatalyzed reaction requires climbing over the mountain-high energy barrier, slow progress. A catalyst is like a tunnel through the mountain-lower energy barrier, faster progress. The catalyst doesn't change whether a reaction is thermodynamically favourable. It changes how quickly the reaction reaches equilibrium. In systems where reactions are thermodynamically favourable, but kinetically hindered, meaning they should occur based on energy considerations but proceed too slowly to matter catalysts make the impossible practical. Nickel catalyzes several reactions relevant to Venus's atmospheric chemistry. The most significant is the water-gas shift reaction: carbon monoxide plus water-producing carbon dioxide plus hydrogen. Venus's atmosphere now contains elevated concentrations of carbon monoxide delivered by the comet, and it contains water in the cloud droplets. Under normal circumstances, these molecules could coexist indefinitely without reacting significantly, because the activation energy for the water gas shift is too high at Venus's temperatures. But in the presence of nickel catalyst, the reaction becomes viable. Nickel provides a surface or coordination geometry where CO and water molecules can adsorb adjacent to each other, react, and release the products. The significance isn't immediately obvious until you think through the implications. Carbon dioxide produced through this reaction is denser than carbon monoxide. It affects local atmospheric dynamics more. CO2 means slightly different buoyancy and pressure profiles in the droplet vicinity. Hydrogen produced is extremely light. It's the one molecule that can escape Venus's gravity entirely if it reaches high enough altitudes. Hydrogen escaping from Venus represents a net loss of atmospheric mass tiny on individual reaction scales, but potentially measurable if the catalyzed reaction proceeds extensively across many droplets. More importantly, hydrogen is reactive. Before it escapes, it can participate in reduction reactions, where it donates electrons to other molecules. Sulfuric acid can be reduced by hydrogen in the presence of catalysts, producing sulfur dioxide and water. Organic molecules can be reduced, altering their structures and producing different compounds with different chemical behaviours. Nickel also catalyses Fischer-Tropsch type reactions processes, where carbon monoxide and hydrogen combine to form longer-chain hydrocarbons or organic molecules. These reactions require high temperatures and pressures in industrial settings, but catalysts dramatically lower the required conditions. Venus's clouds aren't ideal for Fischer-Tropsch chemistry by any means, but the presence of nickel, CO, and hydrogen creates the ingredients. In droplets where concentrations are elevated and temperatures happen to be favourable, perhaps in regions undergoing compression as air descends, the reaction might proceed at measurable rates. The products would be longer-chain organics, molecules more complex than the simple precursors delivered by the comet. Beyond specific named reactions, nickel catalyses general condensation and rearrangement reactions involving organic molecules. If amino acids are present in a droplet alongside nickel ions, the nickel can facilitate peptide bond formation, the linkage of amino acids into short peptide chains. If nucleotide precursors are present, nickel can catalyse their condensation into longer structures. This is precisely the role nickel-containing enzymes play in Earth biology. Enzymes are biological catalysts, and many use metal ions like nickel at their active sites to scaffold and accelerate reactions. Venus's cloud droplets don't have enzymes, but they now have nickel ions dissolved in solution, and those ions can perform similar though less efficient catalytic functions. The concentration of nickel in Venus's clouds after 3I-ATLAS's delivery is estimated at parts per billion levels. That's extraordinarily low by industrial standards, but biology operates at similar concentrations. Enzymes in cells are typically present at parts per million to parts per billion concentrations, yet they drive all cellular chemistry. The key is turnover. A single catalyst molecule can facilitate thousands or millions of reactions before being deactivated. Nickel in Venus's clouds has that same potential. A single nickel ion dissolved in a droplet can catalyse multiple reactions involving different molecules over the weeks. It remains active before the droplet precipitates, or the nickel reacts away into unreactive forms. The question becomes, does nickel catalysis in Venus's clouds actually produce measurable increases in chemical complexity? The theoretical answer is yes. Catalysis accelerates reactions that are thermodynamically favourable but kinetically hindered. The practical answer depends on specifics we don't yet know: the exact concentration of nickel in droplets, the local concentrations of reactant molecules like CO and HCN-derived products, the temperature profiles droplets experience as they circulate, and the residence time of nickel in catalytically active forms before it's oxidized or bound into unreactive compounds. These are parameters the Akatsuki data might reveal, or that modelling studies can estimate. But the mechanism is sound. The chemistry is real. Nickel is present. The conditions allow catalysis. The only question is scale. What makes this particularly fascinating is the parallel to how life uses catalysis. Every living cell relies on metal catalysts, iron, nickel, cobalt, molybdenum, copper, to drive the chemistry that wouldn't occur fast enough otherwise. The origin of life almost certainly required access to catalytic surfaces or metal ions that could accelerate the formation of more complex molecules from simple precursors. Venus's clouds, enriched with nickel from an interstellar comet, are now experiencing a version of that process. Not biological, not intentional, not guided, but catalytic. And catalysis is one of the key mechanisms that separates complex chemistry from random mixtures of molecules. Venus's atmospheric chemistry was already interesting because the organic precursors delivered by the comet can survive in sulfuric acid. Add catalysis, and it becomes more interesting still. Now the chemistry isn't just surviving, it's being accelerated, organised and pushed toward complexity at rates faster than purely thermal processes would allow. The sulfuric acid droplets circulating through Venus's upper atmosphere are operating as billions of tiny chemical experiments, each testing whether catalytic nickel can drive reactions that produce unexpected products. Most experiments will be null results, nothing interesting forms, but chemistry is a numbers game. With enough parallel experiments, even low probability outcomes occur somewhere, and Venus is running this experiment at massive scale, across billions of droplets, for weeks to months as the comet delivered materials circulate and gradually photodissociate. The outcome is unknown. We're not observing this in real time with direct molecular sampling. We're inferring what must be happening based on chemistry we understand and materials we know arrived. But the framework is clear. Venus's clouds are currently enriched with catalytic nickel, prebiotic organic molecules, and energy input from solar radiation. Those are ingredients for complexity. Whether complexity actually emerges is what the data will tell us. But the possibility exists, and that possibility is being explored right now in Venus's atmosphere, whether we're watching closely or not. The chemistry doesn't wait for our instruments to be ready or our papers to be published. It proceeds according to its own rules, and those rules now include catalysis provided by nickel from an interstellar comet. That's the gift 3I-ATLAS gave Venus, not just raw materials, but the tools to do something interesting with them. Venus responded by processing. The materials arrived on November 3rd directly into an active churning atmosphere. There was no cold surface to archive them. There was no stable ice to preserve them. The chemistry began immediately. Hydrogen cyanide started hydrolyzing into ammonia and formic acid within hours. Water mixed with sulfuric acid and changed cloud droplet composition. Nickel dissolved into acid solutions and acquired catalytic roles. Atmospheric circulation distributed everything globally within days. Photochemistry began breaking down the novel molecules within days to weeks. Venus is an alchemist. It takes whatever arrives and immediately begins transforming it, processing it through circulation and chemistry, producing new compounds, and gradually eliminating the perturbation as reactions proceed to equilibrium or photochemical destruction. The timescales are radically different. Mars's interaction with 3I-ATLAS's delivery is measured in years. The materials deposited in October 2025 will remain largely unchanged until robotic excavation begins in mid-2027, roughly 20 months of waiting. Even after excavation, the transformation proceeds over years, as industrial processes gradually convert regolith into useful materials. Venus's interaction is measured in weeks to months. The chemistry is active now. The transformations are ongoing. By January or February 2026, much of the comet-delivered chemistry will have been photodissociated or circulated to background concentrations. The perturbation will fade naturally without external intervention. The mechanisms differ fundamentally. Mars involves technology. The interesting interactions, the catalytic acceleration of reactions, the unexpected optimization of resource processing, the exploration of chemical complexity all require robotic systems to excavate and heat the materials. Absent human technology, Mars simply stores the comet's delivery indefinitely. Venus requires no technology. The atmospheric circulation, the cloud chemistry, the photochemistry, all are natural processes operating continuously. Venus explores the comet's chemistry through purely natural mechanisms. No robots needed, no excavation, no industrial heating. Just planetary scale atmospheric dynamics doing what it always does, but with new ingredients. From an astrobiology perspective, both scenarios are fascinating for different reasons. Mars represents a hybrid scenario where spontaneous chemistry meets artificial acceleration. The question there is, what happens when industrial-scale energy and AI optimization are applied to regolith that happens to contain prebiotic precursors and catalytic metals? Venus represents a pure natural experiment. Given prebiotic precursors, an active atmospheric system, and catalytic metals, does complexity emerge spontaneously, without technology, without excavation, without anything except planetary processes operating on chemistry delivered from outside? Venus tests whether atmospheric environments can serve as venues for the chemistry that might eventually lead toward life. The answer has implications for exoplanet studies. If Venus-like atmospheres can support complex organic chemistry, despite their apparent hostility, then atmospheric habitability becomes a broader concept than surface habitability. Neither scenario produces life. Neither transforms Mars or Venus into habitable worlds, but both involve chemical systems responding to external perturbation and exploring new territory. Both test the boundaries of where complexity can emerge. Both provide natural experiments we can observe, measure, and learn from. The fact that we're observing both simultaneously Mars's slow storage and eventual technological interaction, Venus's rapid atmospheric processing, is historically unprecedented. We've never had the instrumentation and presence at multiple planets to observe their responses to the same external delivery in real time. The comparative study hasn't fully begun yet. Mars data from October 3rd through late 2025 is still being processed. Venus data from November 3rd onward is being analysed. The synthesis papers comparing the two planetary responses, modelling what each system is doing with the delivered materials, interpreting what the differences teach us about planetary chemistry, won't appear until 2026. But the framework is established. 2 planets, same source, different responses, one slow and technological, one fast and natural, both potentially revealing about how chemistry operates under extreme conditions when given external inputs. What emerges from this comparison is a recognition that planets are individuals. They don't respond uniformly to the same inputs. Their existing conditions, temperature, atmospheric composition, geological activity, magnetic fields determine how they process external chemistry. Mars's cold inertness transforms it into a preservationist, archiving whatever arrives for future disturbance. Venus's dynamic atmosphere transforms it into a processor, immediately integrating and transforming external inputs through active chemistry. Neither response is better or worse. They're different strategies for handling the same challenge: how to accommodate materials that aren't in equilibrium with existing conditions. And both responses are being documented by human spacecraft and ground-based telescopes. We're watching planetary chemistry unfold across multiple worlds simultaneously. The data is being collected, the observations are being recorded, the analysis will synthesize everything into understanding: what happened, why each planet responded as it did, and what the outcomes teach us about chemistry, planets, and the potential for complexity to emerge when worlds receive gifts from interstellar space. The next year will bring those answers as publications emerge, and the scientific community debates interpretations. Until then, we wait knowing that the processes are active, the chemistry is real, and the story is unfolding whether we're fully observing it or not. Mars is holding. Venus is transforming. And 3I-ATLAS has given both planets materials they haven't encountered in billions of years, setting in motion processes that will occupy scientists and fascinate observers for years to come. We're standing at a specific point in time, late November 2025, and everything that's happened so far is prologue. The comet encountered Venus 3 weeks ago. The materials were delivered. The chemistry began. And now we're in the waiting phase, the period where observations transition to understanding, where data becomes published findings, where speculation gives way to confirmation or refutation. Let me walk you through what's coming over the next 18 months, because the timeline determines when we'll have answers to the questions this entire story has raised. And those answers matter, not just for Venus, not just for Mars, but for how we understand planetary chemistry and the potential for complexity to emerge in extreme environments throughout the universe. Right now, in late November 2025, ground-based observatories are continuing to track 3I-ATLAS as it recedes from the inner solar system. The comet is still visible, still outgassing though at declining rates. Spectroscopic measurements continue documenting water, hydrogen cyanide, carbon monoxide, and nickel emissions. These observations are critical for establishing baseline data. What was the comet producing after perihelion? How rapidly did activity decline? What was the composition stability over time? The telescopes, SWIFT, Keck, major observatories worldwide are building a complete activity profile for 3I-ATLAS that will anchor all subsequent analysis of what the comet delivered to planets. Simultaneously, JAXA's Akatsuki orbiter has completed transmitting the bulk of its Venus encounter data back to Earth. Venus orbiters have limited communication bandwidth, so downlinking a complete dataset from several days of intensive observations takes weeks. By early December 2025, the data should be fully received at JAXA's mission control centers in Japan. Then begins the slow, methodical process of calibration and analysis. Raw instrument data must be corrected for instrumental effects, calibrated against known standards, and processed into scientifically usable formats. This isn't fast work. It's careful, detail-oriented analysis by teams of scientists ensuring data quality before attempting interpretation. Preliminary results might emerge by late December, but comprehensive analysis will take into January and February 2026. What will that data show? If the theoretical framework we've outlined is correct, Akatsuki's spectrometers should detect elevated concentrations of water vapour, hydrogen cyanide, or carbon monoxide in Venus's upper atmosphere during and immediately after the November 3rd encounter. The increases would be subtle parts per billion changes in trace gas concentrations, but detectable if instruments were operating with sufficient sensitivity and looking at the right atmospheric regions. If nickel compounds were present in sufficient quantities, they might show up in particle composition data or through spectral signatures from cloud droplets. If the data shows no significant changes, it indicates either lower capture efficiency than models predicted, faster photochemical destruction than expected, or instrumental sensitivity limitations. Any outcome teaches us something valuable about Venus's atmospheric response to external inputs. January through March 2026 is when the first scientific publications will appear. These papers will be submitted to journals like Icarus, Geophysical Research Letters, Nature Astronomy, or similar planetary science venues. Initial submissions might appear on preprint servers like Arxif in late December 2025, allowing the scientific community early access to findings before formal peer review completes. The papers will address specific questions. Did atmospheric composition change measurably? Were HCN or CO signatures detected? What do cloud droplet composition measurements reveal? How did atmospheric circulation distribute any captured materials? These initial papers won't answer every question, but they'll establish the observational foundation for everything that follows. Simultaneously, detailed analysis of Mars orbital data from the October 3rd encounter will be published. NASA's Mars Reconnaissance Orbiter and ESA's Mars Express have been collecting data for over a month by this point, documenting the southern highlands and polar regions where 3I-ATLAS's materials should have deposited. Spectroscopic measurements from these orbiters can detect nickel enrichment, hydrogen cyanide signatures in ice, or other indicators of cometary material deposition. If confirmed, these papers will validate the Mars deposition model. If signatures are absent or below detection limits, they'll force refinement of capture efficiency estimates and deposition modelling. The media landscape will shift during this January to March window. Scientific findings will be translated into popular science articles and news coverage. The narrative of an interstellar comet altering 2 planetary atmospheres will enter public consciousness more broadly. Some coverage will be accurate and measured, some will be sensationalized. Science communication is always a mixed landscape. But the core story that external chemistry from an interstellar object has perturbed Mars and Venus in measurable ways will gain wider recognition. Public interest drives further observation and funding for follow-up studies, so this media phase, while imperfect, serves an important function in maintaining scientific momentum. April through June 2026 brings the phase of synthesis and modelling. With observational papers published and data available, researchers will build computational models exploring what the observations mean. What chemical reactions should have occurred in Venus's clouds given the observed concentrations? How long should comet-delivered materials persist before photochemistry destroys them? What products should form? How do atmospheric circulation models predict the distribution patterns? These modelling papers complement the observational papers, building a complete picture where theory and observation constrain each other. Discrepancies between models and observations highlight areas where our understanding is incomplete and where further research is needed. This is also the period when mission planners begin incorporating new findings into future mission designs. ESA and NASA are developing concepts for future Venus missions, potential orbiters, with advanced spectrometers, possible atmospheric entry probes, even long-shot sample return concepts. If the 3I-ATLAS encounter revealed unexpected chemistry in Venus's clouds, future missions might be retargeted to study those regions specifically. Similarly, Mars mission planning for post-2027 surface operations will incorporate understanding of how the October 3rd deposition affected regional regolith chemistry. Science is iterative. Observations inform future observations. Understanding builds progressively. The mission proceeds according to its established architecture. But mission scientists are now aware that the landing region might contain chemical signatures from the October 2025 comet encounter. That knowledge informs what measurements to prioritize once systems are operational on Mars. By early 2027, the community has consensus on the broad strokes and documented disagreements on details still under investigation. The data flowing back to Earth efficiency metrics, yield rates, Processing throughput will tell the story indirectly even before scientists realize the connection. Engineers will notice anomalies. Why is water extraction 8% more efficient than simulations predicted? And eventually someone will correlate those anomalies with the October 2025 comet encounter. June 2027 onward is the operational phase where long-term patterns emerge. Months of Mars surface operations generate datasets large enough for statistical analysis. If comet-delivered materials are affecting processing chemistry, the signal will become clear as noise averages out. Publications will appear documenting unexpected findings, enhanced catalytic activity in Mars regolith processing, or detection of interstellar organic signatures in polar ice samples. The Mars and Venus stories that began in October and November 2025 reach their conclusion, or more accurately, reach the point where observations confirm or refute the speculative framework we've built. Simultaneously, Venus atmospheric monitoring continues. Follow-up observations by Akatsuki or future missions will check whether Venus's atmosphere has returned to baseline composition or whether lingering signatures of the comet encounter persist. If organic molecules or unusual chemical patterns are detected months after the encounter, it suggests longer persistence timescales than predicted and raises questions about Venus's capacity to support complex chemistry for extended periods. Comment on papers, share interpretations, ask questions. Science advances through collective scrutiny and discussion. The more people paying attention, the faster insights emerge and the more thoroughly findings are examined for errors or alternative explanations. You're not passive audience to this story. You're part of the community making sense of what an interstellar comet did to two planets in our solar system. This is real science unfolding in real time. The data exists, the observations were made, the chemistry is happening right now, whether we're watching or not. Over the next 18 months, speculation gives way to confirmation, and we'll know definitively whether 3I-ATLAS changed Mars and Venus in the ways theory predicts. The comet arrived from beyond our solar system carrying materials forged in another stellar environment billions of years ago. It passed through our inner solar system for a few brief weeks and delivered those materials to two planets with radically different environments. Those planets are now processing that delivery, one slowly through storage and eventual technological excavation, one rapidly through active atmospheric chemistry. Both are teaching us about planetary systems, about chemistry under extreme conditions, and about how complexity can emerge when worlds receive gifts from interstellar space. Stay curious, stay engaged. The answers are coming, and when they arrive, we'll understand not just what 3I-ATLAS did, but what planets do when they encounter chemistry from beyond their own systems, chemistry that hasn't been part of their evolution, chemistry that forces them to respond, adapt, and explore pathways they've never travelled before. That's the story we're living through. That's the discovery unfolding across the solar system right now, and you're here at the beginning, watching it happen.